What's up, guys? Yeah, so let's keep it talking about our introduction to topology. Okay, and let me just quickly review that previously that the topological space X, basically you got some subset of power sets, and you claim that these guys are just the people call it open set, satisfy these three properties, such that the empty space, and the empty set and the whole space belongs to open, and the collection, the finite, the countable union, the finite collection of the open set will be the open set. Okay, so hopefully this is okay. Now let's talk about continuity. Okay, I think most of these kind of results that I already proved in the analysis, so I will post my analysis video below if you haven't seen the proof. Okay, so remember in the calculus that the definition means that let's say for epsilon greater than 0, there is delta greater than 0, such that when x minus x0 less than delta, and f of x minus f of x0 less than epsilon. Okay, so this is the definition of continuous at x zeros. If you take a set and each point is continuous, then we say that f is continuous on that set. Okay, so let's talk about the topological definition. So somebody give you two topological space x and y, and that's so there will be some open set of x, open set of y. So definition is that for every open in y, let's say G in y, f inverse G is opening. Then we call f is continuous on x. Okay, so inverse open, opens and inverse is open. Okay, so obviously it's different. So this is trivial that f of xy is continuous if and only if for every closed set C, f inverse C is also closed. Okay, this is trivial. Okay, so proof just one line because previously we got open, right? So we can check that if y delete C will be the same f inverse, or y delete C will be f inverse x will be x delete f inverse C. Okay, so you can check this, right? This is for every set. So if you put every open set, the complement is closed, and it transforms in the right hand side. Okay. Okay, and yeah, this is continuous. And let me talk about homeomorphism. Okay, so this is also an important topic. Let me just give you a favor, and I will come back to this in the future. Okay, so homeomorphism is like the common, the most basic terminology that we want to say that two topological spaces are the same, right? So in the mathematics, that some people like to say that vector space are isomorphism, abelian group are isomorphism, ring are isomorphism. So homeomorphism, people like to say that the two topological spaces are the same. Okay. So before that's definition. So let's say f map to. So usually, okay. So let me just definition. So f, let's say we got a function between two topological space, and such that the first one is that f is a 1, 1 on 2, and continuous. So this is also called a continuous bijection. Okay. And the second is that f has continuous inverse. Inverse. So by definition, since it's bijective, so f inverse will exist. Okay, so if f satisfies these two, and then we say f is a homeomorphism. F is a homeomorphism. Homeomorphism. Okay, so this is one type of this is usually one type of definition of homeomorphism. Okay, then we said x and y are homeomorphic. So now I'm talking about a two space, right? Homeomorphic. If there is a continuous map, let's say there becomes a continuous map and another continuous map G from y to x, such that f circle G So G map to G to F, right? So let's say F circle G is identity on Y, and the G circle F is identity on X. Okay. So this is the definition. So we say F, X, Y homeomorphic if there's a, if I can find F and G. Okay. Moreover what? Moreover is that FG. So FG not just satisfy this. FG must be homeomorphism. Must be homeomorphism. And the inverse of each other. Okay, so you can see that this is just another definition that basically when I say X and Y are homeomorphic, I just say that there exists homeomorphism between them. And if there is a homeomorphism between them, then it must be home. Then I can say that X and Y are homeomorphic because F and F inverse that replace F and G. Okay. So fact, this is also trivial that homeomorphism forms equivalent class or equivalent relation. Okay, so what it means that X is homeo. So okay, so I use this notation. S is homeomorphic to X, which is trivial, right? So trivial because you can choose F to be identity. Okay, and if X is homeomorphic to Y, then the Y will homeomorphic to X. So proof is also trivial because you can replace F to be F inverse. Okay, and the third is that if X is homeomorphic to Y, Y homeomorphic to X, Z, then X is homeomorphic to Z. Okay, so use function composition. Let's say you got F and G, so you can take G circle F. Okay. Okay, so let me just talk about examples. Okay, so the simple example will be, let's say, the first one is that the real number is homeomorphic to any open interval. Okay, so any open interval. Okay, any open interval. Okay, so that means every open interval are homeomorphic to each other. Okay, maybe let's see some simple example. Let's say X is -1, 1, and Y is 0, 5, right? And the simple map will be linear, right? So I think this is trivial that everybody can come up with. So you can define f of x to be phi half x, x plus 1, right? So you can check that this is 1, 1 on 2, right? This is trivial because it is linear, and so it must be continuous, and then the inverse exists. Okay, and also one can also check that maybe it's not obviously, but actually the okay, and actually maybe the 0, 1 open is also 1 to infinity homeomorphic. Reason is that you can choose f of x to be 1 divided by 1 over x, right? So which means it's this, right? So which is homeomorphic. This is 1, 1 on 2, right? Because for each one that you find something, except for 0 points, and that is also continuous. Okay. And also let's say example 3 is that the -1, 1 is homeomorphic to real number. So this is another proof that basically the people like to say that the 0, the -1, 1 has the same cardinality as the real number. Okay, so this is using the so-called famous arctangent map. So if you take the arctangent map x divided by 2 divided by pi, let's say this is f of x, and this is f and x, and you can easily see that when x goes to infinity, then become pi over 2, right? So I become 1, right? So it's this 1 and -1. Okay, and you can see that in this region, right, this is 1, 1, 1, 1 on 2. Right, so this is 1, 1 on 2, right? Right, so which establish this homeomorphism because I can take this is f. I can take this is f. Okay. 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 So final results. I think there is some several examples. Okay, there are some. Okay, so let's still keep talking about examples. Yeah, so let's say example 4 will be let's see, you take this 1111, right, and try to compute as count to do the homeomorphic to find a sphere as 1. Okay, so this is very simple that you can check by yourself. So I'm a little bit lazy, but you can check. Okay, and yeah, I think that's okay. And another is that okay, that's called this is called a stereo projection. So basically, you can, if you basically, what I'm saying is that somebody give you a plane, right? So you start from plane and you model, you delete 1 point, right? So you delete 1 point, right? So let's say this, right? Put 1 point here. Okay, so you can see that if you draw a ball, right, and you put here 0, 0, let's say 1, and then you draw a shine line, right? You shine a line. Right, so shine a line, right? So each guy in the ball will hit some points in R, right? Each guy in the ball will hit some point in R, will hit some unique point, right? So which means that, and then each plane, right? Each plane can hit can also send this, right? So basically, this stereo or projection give you a map, let's say, from a sphere, right? Sphere has 2 model points, right? Except for this null pole. And give you homeomorphic to the plane. But this is also called a 1-point compactification. So if you put the real plane, you put the 1-point compactification. So basically, you identify all the infinite point, like the infinite point as another point, and you then you somehow wrap your plane becomes a sphere. Okay, so this is also homeomorphism. You can just see the picture. Okay, so it's trivial, right? But it's a little bit tricky to write down this map. You can try to write yourself, right? But it's not difficult. Okay, I think it's okay. Okay, so let me say something about the theorem about homeomorphism, and we can finish this video. So theorems on homeomorphism. Let's see. Okay, I guess it is trivial. Okay, so proof. Sorry, let me just about theorem. So what I'm saying is that let's say you get some homeomorphism x to y, and another homeomorphism g to y to z, and then you can check that G circle F is also homeomorphism. Homeo. Okay, so the proof is also proof is almost trivial, right? Because this is 1 1 onto bijection. So G circle F is also 1 1 onto by 1 1 onto, and F is continuous, G is continuous. So the composition continuous, and the G circle F will be F inverse G inverse, right? So both will be continuous because F inverse and G inverse are continuous, so their composition must be continuous. Okay, you can check by your check the rest. Okay, and also the one thing I want to mention is that in the future I will talk about more about like the Hausdorffness or compactness or contentness. So connectedness and Hausdorff and all these property will be preserved respect to homeomorphism. For example, if X is Hausdorff, then if F is a homeomorphism between X and Y, then Y will be Hausdorff. So if X is Hausdorff, Y will be Hausdorff. And vice versa if there's a if they are homeomorphic. So every time when I say homeomorphism, that you can believe that these two topological spaces are the same as topological space. Okay, so see you guys in next videos.